Lesson 17. In this lesson, we're going to simplify radicals. I want to remind you that in a radical there are two parts. There is the index, which tells you what root it is, like a square root or a cube root, and the radicand, which is the number on the inside. So throughout this video, I will refer to the radicand and the index. We're going to start by simplifying a square root of 20. A square root is simplified when the radicand, that's the number inside, has no square factors except 1. The square root of 20 is what we call an irrational number. When you try it on your calculator, here, let me call up a calculator and let's do it. So I'm going to enter 20 and take the square root, and you see this long, non-terminating, non-repeating decimal. That is an irrational number because we can't express it exactly as a fraction or decimal. So all we can do to the square root of 20 is either get a decimal and round it to estimate it, or we can simplify it. And so again, I'll read the definition. A square root is simplified when the radicand has no square factors except 1. Now, factors are numbers that are multiplied. So let's talk about square factors. 4, 9, 16, 25, 36, 49, 64, 81, and 100. That's 2 to the second, 3 to the second, 4 to the second, 5 to the second, 6 to the second, 7 to the second, 8 to the second, 9 to the second, and 10 to the second. And of course, 1 to the second is a perfect square, but it says other than 1. So we don't care that much about 1. It won't do us any good. I have to look at this list and see if any of these numbers will divide evenly into 20. Well, 4 is the only one. So 20 is not simplified because it can be written as 4 times 5. Now what we do now is, because these are factors, they're being multiplied, we can separate them. Now if these are terms added, we cannot separate them, but because they're multiplied we can. And so the square root of 4 is 2, and then that's times the square root of 5. And this is considered the simplified form of the square root of 20. Number 2, the square root of 50x to the 6th. So the square root of 50 is an irrational number. When I take the square root, again, I get this long, non-terminating, non-repeating decimal. So that can only be simplified. You can't express it exactly. I have to look for squares that go into 50. And so I go to my list and I go, 25 goes into 50. So that's 2 times 25. And x to the 6 is a perfect square because remember that when you have the root of a variable that's a base with an exponent, you just divide that exponent by that root. So we're going to divide 6 by 2 and it goes in there evenly. So I can separate, but I'm just going to take out these perfect squares. The square root of 25 is 5. 2, index 2 goes into 6 3 times. And so the 25 came out because it was a perfect square. The x to the 6 came out because it was a perfect square, and the only thing left is a radicand of 2, the square root of 2. So the final answer is 5x to the 3rd times the square root of 2. Now let's talk about reducing a cube root. A cube root is simplified if its radicand contains no cubed factors except 1. So now we need to know perfect cubes. So 2 to the 3rd is 8. 3 to the third is 27. 4 to the third is 64. 5 to the third is 125. 6 to the third is 216. They get big really fast. 7 to the third is 343. 8 to the third is 512. 9 to the third is 729. And 10 to the third is 1000. So we're looking for factors that are cubes that will go into 24, and that's only going to be this 8. So my cube root of 24 can be rewritten as the cube root of 8 times 3. And the cube root of 8 is 2, and then I have my index of 3 and a 3 radicand left inside. So the cube root of 24 in simplified form is 2 times the cube root of 3. Don't forget to write the index. The only time we don't write an index is when it is a square root. Now we have the cube root of u to the 13. And 3 won't go into 13 evenly. So what we have to do is we have to divide 3 into 13. Okay, that goes 4 times with 1 left over. So I'm going to rewrite this as the cube root of u to the 12th times u. There's 1 left over, so that tells me that that 1 is the extra one that makes it not a perfect cube. See, 3 goes into 12 exactly 4 times. So u to the 4th cube root of u. So we divide the 3 into the 13. It goes 4 times, and look, that's your exponent on the outside, and there's a remainder of 1, that's your exponent on the inside. So you don't have to actually write the u to the 12 times 1, but that's what you're doing. You're taking out the perfect square, which is u to the 12th, because 3 goes evenly into 12. Number 5, the cube root of 24 y to the 4th. So 24 has an 8 in it, so that's going to be an 8 times 3. Y to the 4th, well, 3 goes into 4 one time with 1 left over, so I'm going to need to write it y to the 3rd with the 1 that's left over, and then I can take the cube root of the 8, because it's a perfect cube, and the cube root of the y cubed, and that's going to give me 2y to the 1, and of course you don't write that 1, but I'm going to do it there for now. Cube root of 3y to the 1. And I don't think Alex is going to like it if you write the 1, so let's just not write those 1s, but that's what's understood to be there. So the cube root of 24y to the 4th reduces to 2y times the cube root of 3y. So whenever you're reducing a radical, you have to break its radicand into factors, that's things that are multiplied, where they contain perfect cubes if it's a cube root, or perfect squares if it's a square root, and you might even see a 4th root. So you have to find powers of 4 that go into your radicand. All right, so let's talk about the rules of addition of radicals. And this is going to be the same as subtraction as well. Okay, 3 things have to be true in order to add or subtract radicals. IRV. I call it the IRV rule. In order to add or subtract, radicals have to have the same index. The same index. They must have the same radicands. And they must have the same variables inside and outside. So ask yourself, do you have IRV? IRV, IRV. So when I have something like 8 square root of 2 minus 5 square root of 2, I'm going to look at IRV. Do they have the same index? Yes, they are both square roots. Do they have the same radicands? Yes, they're both 2. Do they have the same variables? Yes, they don't have any variables. So all I do to subtract these is to subtract the 8 minus 5 and bring over my radical. 8 of those minus 5 of those are 3 of those. Whatever's in the radical stays the same. Number 7. 3 square root of 75 plus 4 square root of 3 minus square root of 27. Do we have IRV? Well, no, we don't, because look, they're all square roots. They don't have any variables, but look at your radicands. One is a 75, the next one is a 3, and the last one is a 27. Okay? So I need to simplify these to see if I can make them match. So 75, I'm going to write it as 25 times 3 because 25 is a perfect square factor of 75. 4 square root of 3, I'm going to leave it because 3 has no square factors except 1. And 27 is 9 times 3. 9 is a perfect square factor of 27. So now I'm going to bring out the squares and I'm going to multiply them times what is outside. So that's going to be a 3 times 5 square root of 3 plus a 4 square root of 3. And the 9 can come outside, so that'll be minus a 3 square root of 3. Now 3 times 5 is going to give me a 15 square root of 3. Then I have a plus 4 square root of 3 and a minus 3 square root of 3. And now all of a sudden I do have IRV. They have the same index because they are all square roots. They have the same radicands. The radicand of each of these terms is 3. And they have the same variables because they have no variables. So all I do is say 15 plus 4 minus 3. That's 19 minus 3, which gives me 16 square root of 3. Number 8, the square root of 18w plus the square root of 50w. Well, when I first look at this, I say I can't add these together because they have different radicands. One has an 18w, one has a 50w. They do have the same index, they're both square roots. They do have the same variables, a w inside. I need to simplify these. 9 times 2 times w plus the 50 can be 25 times 2 times w. 9 is a perfect square factor of 18. 25 is a perfect square factor of 50. The 9 square root can come outside as a 3, leaving a 2w as the radicand. The square root of 25 can come out as a 5, leaving a 2w as the radicand. And now look, index is 2, radicands are both 2w, variables, w inside. This is 8 times the square root of 2w. When you add, you do not change the radicands. You just bring them over. Number 9. The square root of 8z cubed plus 2z times the square root of 72z. I have the same index. These are both square roots. But look, my variables are all over the place. A z cubed inside one, and a z out, and a z in the other. And the radicands aren't the same either, 8z cubed and 72z. So I need to reduce these or simplify these and see if I can make a match. If I can't make a match, I can't add them. 8 is 4 times 2. The perfect square factor in 8 is 4. And then I've got a z cubed. And then I've got a 2z. And 72 is actually 36 times 2z. The perfect squares can come outside. And look, z cubed is not a perfect square. 2 goes into 3 one time. So what I've got to do is I've got to change this z cubed to a z square and a z to the 1. Because now I can take out the 4, take out the z squared, take out the 36. Those are all perfect squares. So I get 2z square root of 2z plus 2z times 6 square root of 2z. The 4 came out as a 2. The z squared came out as a z to the 1. Look, 2 goes into 2 one time. Or, think of it this way. 2 goes into 3 one time with 1 left over. Then I have to multiply this 2z times 6. So let's finish it up so we can add these together. 2z square root of 2z plus 12z square root of 2z. And be careful with your z's. Notice how I put a line through them so they don't look like 2's. Now let's talk about IRV. Do they have the same index? Yes, they're both square roots. Do they have the same radicands? Yes, they're both 2z. Do they have the same variables outside and inside? They sure do. They both have a z outside and a z inside. So all I do is I add the 2 and the 12 and I get 14z square root of 2z. That's the answer to number 9. Number 10, we're going to have to deal with a fourth. Look, we've got a fourth root, -3, index 4, so fourth root of 32, minus the fourth root of 162. Now, I don't have my fourths memorized, so I'm going to get my calculator out, and I'm going to do 1 to the 4th power. Well, that's 1. Okay, that's not going to help me. 2 to the 4th power is 16. 3 to the 4th power is 81. 4 to the 4th power is 256. Now, I don't need to go any more on this problem because 256 is bigger than both of my radicands. So my numbers have to have the factors of 16 and 81 in them if they are containing perfect fourth factors. So it turns out that 32 is 16 times 2. And 162 is 81 times 2. So the fourth root of 16 is 2. So that's going to be a negative 3 times a 2, fourth root, 2 left inside, minus 3, fourth root of 2. Now on your calculator, to do the fourth root of 81, you have to press a 4, the second key, and the caret key. Okay, so this is negative 6, fourth root of 2, minus 3, fourth root of 2. And now all of a sudden I do have IRV. They both have index of 4. They both have a radicand of 2. And they both have no variables, so the variables match because there are none. So minus 6 minus 3 is going to give me minus 9, fourth root of 2. And that's my final answer for number 10. And number 11, negative cube root of 108x to the fourth plus 2 cube root of 32x to the fourth. I need to think of my cubes other than 1. 1 cubed is 1. It won't do us any good. 2 cubed is 8. 3 cubed is 27. 4 to the third is 64. 4 to the third is 64. 5 to the third, you can do these on your calculators, 125. I don't need to go anymore because my radicands are both less than 125. So I'm going to check and see which one of these goes into 108. I'm going to take my calculator and look. 125 is not going to go into 108. I mean, you could try it, but it's not going to go. I'm going to try 64. So I'm going to take 108 and I'm going to divide it by 64. Look, it doesn't go evenly, so that's not it. So I'm going to take 108 and I'm going to divide it by 27. And it goes 4 times. So it's 27 times 4. So remember, when I do my variable into my exponent, I'm going to divide it. So it's going to have 1 left over, so there's going to be 1 left in here. So I need an x to the third and a x to the 1 for that. Over here, 32 is 8 times 4. 8's a perfect cube. And again, I'm going to have an x to the third and an x to the 1. Okay? Cube roots of perfect cubes can come outside. 27 and x to the third can come outside. 8 and x to the third can come outside because they're perfect cubes. So there's a negative here, so there's going to be a negative 3 and an x, because look, the index 3 goes into the exponent 3 one time, leaving inside my cube root a 4x. And so in the second one, the 2 is outside and a cube root of 8 comes out as a 2, and the cube root of x to the third comes out as x, and that's going to leave me with a 4x x to the 1 on the inside, or just 4x. So again, you can think of that as 3 index goes into the exponent 4 one time with 1 left over. Okay? Or you can split it up, x to the third, x to the 1, and 3 goes into 3 one time with 1 left over. So all that's left to do is to multiply what's outside this second radical, 4x cube root of 4x. Now be careful. My index over here is dangerously close to looking like an exponent, so I'm gonna correct that. Even though it's kind of in the right place, you got to be careful because you'll think that's an x to the third. That's a cube root, and this cube root needs to be down in here so you know it's a root and not the exponent on this x that's outside. So be really careful. Now look, Irv, do they have the same index? Yes, they're both cube roots. Do they have the same radicands? Yes, they're both 4x. Do they have the same variables outside and inside? Yes, they both have an x outside and an x inside. So that means that I can combine these just by combining the numbers. Negative 3 plus 4 is positive 1 x cube root of 4x. And if you write that 1, Alex is going to tell you you don't need it. It won't matter to me if you write it, but Alex will count it. I think it might take it in the homework, but it might count it wrong on the quizzes, so be careful. So that is simplifying and adding and subtracting radicals.